Welcome to the lecture number 7 of Physics 401A. In this lecture, we will mostly discuss different properties of Lagrangian formulation. We start by discussing the very concept of cyclic coordinates. If we recall the Euler-Lagrange equation, then we can say that ddt of del L del Qy dot minus del L del Qy is equal to 0, where L is the Lagrangian of a system, T is time, and Qy is the ith generalized coordinate, and Qy dot is the corresponding generalized velocity. Okay, and I ranges from 1 to n, small n, where small n is the number of degrees of freedom of the system. Now, if the Lagrangian is independent of a coordinate qk, that means qk does not appear explicitly in the expression of the Lagrangian, then we can easily say del L del qk is equal to 0. Then this term, just a sec, so this term will be 0, and in order that this equation be valid, this term will also be 0, right? And that simply says that ddt of del L del Qk dot is equal to 0, and del L del Qk dot is a constant of motion. Okay. Now, this case where Qk does not appear explicitly in the expression of Lagrangian is called a cyclic coordinate, and Pk, which is defined as del L del Qk dot, which becomes as a constant or invariant of motion, is known as the conjugate momentum of Qk. Okay. Now remember, if both Qk and Qk dot do not appear in the expression of the Lagrangian, then there is no story of cyclic coordinate as such, because then it will be 0, this term will be 0, and this term will also be 0. So 0 minus 0 is 0, that is, a trivial identity. Okay. Only when qk is absent in the Lagrangian but qk dot is present, then only this question of cyclic, the context of cyclic coordinates comes, and then only we can also define the conjugate momentum as well. Okay. Let us take, for example, the case of a particle moving under a central force F of r is equal to minus k by r square. So this is an attractive inverse square law, and the particle in general we know that will move in a plane, so we simply choose for simplicity 2D plane polar coordinates, and the Lagrangian will be half m r dot square plus r square theta dot square minus vr. Okay. Then we can write this is equal to half m r dot square plus r square theta dot square plus k by r, as we all know that minus dvdr is equal to force, which is given minus k by r square. So just by integrating you will have v is equal to minus k by r plus some arbitrary constant of integration. Now just setting the reference level of the potential v at infinity, that means at r is equal to r tends to infinity, v is 0, we can make c to be 0, and v is simply minus k by r. Okay. So L will then have this expression. Okay. Now observe that L does not explicitly contain theta, although it contains theta dot. For r we don't have any such story, because both r and r dot, they appear in the form of Lagrangian, in the expression of Lagrangian. So theta is not there, but theta dot is there. That's why theta is a cyclic coordinate, and p theta, which is nothing but del L del theta dot, is equal to mr square theta dot, is the conjugate momentum of theta and is a constant of motion. Okay. As you all can understand, this is nothing but the magnitude of the angular momentum of the system, of the particle. Okay. Now we talk about a very interesting property, that is additivity and scaling of Lagrangian. Let's have a look at the Euler-Lagrange equation. ddt of del L del Q I dot minus del L del Qi is equal to 0. Now we assume a system which is consisting of two subparts. A and B having no mutual interaction between them. And also they are characterized by LA, QA, QA dot, QT, and LB, which is a function of QB, QB dot, and T, okay, respectively. Now let's say that there is a box of particles, and the two box I can put a compartment, an impermeable compartment or a totally isolated compartment, which basically divides the whole system in two, and making all sort of interactions between those particles prohibited. Although all the particles inside one compartment, they are interacting within themselves, and also in the other compartment the particles are interacting among themselves, but one compartment is not interacting with the other. That is the story. Then for, let's say, for the side A, we can write ddt of del LA del QAI dot minus del LA by del QAI is equal to 0, where I denotes 1. I can range from 1 to n capital A, where n capital A is the number of degrees of freedom for the compartment A, right? And here you can see that LA is the Lagrangian of the compartment A. Okay. Here we have assumed that the Lagrangian can already be defined, and we know somehow the Lagrangian is there, and this is a function of QA, QA dot, and T. Okay. Similarly, for B, we also assume that a Lagrangian is defined in usual sense, and we have a similar type of equation like this: ddt of del LB del QBI dot minus del LB del QBI is equal to 0. Okay. Now these QAs and QBs, they are mutually independent and distinct set of variables, because one is not at all seeing the other, right? There is no intermediate, how to say that, intercompartmental interaction. There is no interdependence. Okay, so for all I, we can easily say that let's say that delta LA delta QBI dot is equal to 0, and delta LA delta QBI is equal to also 0. That means LA is independent of QBI and QBI dot. Similarly for del LB and QAI and QAI dot. Okay. Now our question is, if we know LA and LB, can we propose a representative Lagrangian for the whole system? Of course, you can say yes, we can propose the Lagrangian should be an arbitrary linear combination of the two. Let's say alpha LA plus beta LB, where alpha and beta, they are constants. Now the thing is that, and that there is actually no problem if you just notice this carefully. If you multiply the whole thing by alpha, this will still be valid, and if you multiply the whole thing by beta, it will still be valid. And then you can say that as this Lagrangian of compartment A is independent of the generalized coordinates and velocities of B, and the same thing for the Lagrangian of B with respect to the coordinates and velocities of compartment A, finally we can always write ddt of del L del Qy dot minus del L del Qy is equal to 0 for the whole system Lagrangian L, where L is alpha LA plus beta LB. Remember, I am not saying LA plus LB, I am simply saying alpha LA plus beta LB, right? But here the I will range from 1 to up to NA plus NB. Now the total degrees of freedom will be just the sum of the degrees of freedom of the two non-interacting system. Now remember the case, and that is exactly what I said here, so that from equation 1 one can easily note that EL equation is unchanged if Lagrangian is multiplied by a constant factor, right? So if a system consists of more than one subparts, for every subpart Lagrangian, the corresponding EL remains invariant under the multiplication of an arbitrary constant, right? So that's why there is no prior, like prior restriction by which one can say, well, L cannot be equal to alpha LA plus beta LB. Now the only thing is, let's say we have a compartment of gas of molecules of gas molecules, and someone has made some wooden partition so that they are no longer interacting. The two compartments are totally separated. Now let's say someone is lifting the separator. Okay, if we lift the wooden separator, then these particles will mix. But now let's say these are the particles of ideal gas. So simply, as you can understand, that there were no interaction, even if there is, irrespective of whether there is a wooden separator or not. In general, the particles are, unless the collisions are there, the particles are non-interacting. Okay. Now let's say the collisions, the collisional free path is very, very much greater with respect to the very much greater with respect to the how to say, the very much greater, but what I am trying to say is that it is comparable to the, so the number of collisions basically is very much less. So that means the collisional free path is comparable with the system size. So for this reason, the system can be said that very weakly collisional. Okay, if the system is weakly collisional, then basically the collisions are almost neglected, and the the total system of the gas molecules are almost considered as they're considered as a system of molecules without interaction. Now you know that when you lift the wooden separator, then specifically the system is just one system, and there is no reason that one should be, the Lagrangian of something has some arbitrary constant multiplied by alpha and arbitrary constant multiplied by beta, because the system would not distinguish the compartment A and B any longer, right? So now try to understand, then the most reasonable choice is LA is equal to simply LA plus LB. Another thing is that although we are talking here without making any clear mention of what type of quantity Lagrangian can be, it is somehow inside our mind that Lagrangian has something like energy. Okay, and energy is simply an additive quantity. Okay, that means if you know about the extensive properties in the context of thermodynamics, so energy is nothing but the extensive property. Okay, so Lagrangian can also be expected to be an extensive property. An extensive property are simply additive. They are not like when let's say the system is divided into n subparts, and for every subpart the energy is U1, E2 up to En, and then you don't say that the total energy is alpha E1 plus beta E2 like this, but you just say E is equal to E1 plus E2 like this up to En. So that was also somehow inside our mind. Okay, but when the people did the formulation, that was also inside their mind. But the most reasonable thing, what I feel personally, is that if you just think of this partition and the lifting of the partition, then it would be reasonable to understand that why L is simply LA plus LB. Or if it has more than one subpart, then it will be a summation over LIs. Okay, where I will denote the index of the number of the subparts or the compartments. Okay. Now that's why it is just, I am saying that if we now remember, so if you now just admit the additive rule, then we can simply say that the arbitrary constants will not be arbitrary anymore. They all have to be either same, either one or at least all of them should be multiplied by, so LA should be, if LA is multiplied by alpha, that should also be multiplied by alpha, so that here we will simply have a global multiplication of L with alpha. And this is also possible, that is no problem over there. If we have a global multiplication factor, then we can define this multiplication as a different choice of unit system, and the problem is solved. Okay. Now we try to understand finally that can we extract the concept of energy from Lagrangian, at least for our very familiar classical mechanical systems. So one, we saw that if we start from Newton's law, Newton's second law, of course L for conservative force fields and velocity independent potential fields, L becomes simply T minus V. Then also we showed some extension of this. Okay, but if we don't use Newton's second law, for example, here don't use, can we have some more general expression of something, of some conservation principle or something which can later be related to the energy directly? So if we to be very honest, so Lagrangian is T minus V. So this is the difference between two type of energy, but this does not say about how it is related to the total energy. That means, let's say T plus V. So here in this context we will discuss this. So Lagrangian is a function of q dot t in general. Of course, here we are just, again for simplicity, we are taking one dimensional problem. That means only one set of q dot. You can easily generalize for multi-dimensional problem. Then you will simply have to write the summations. Okay, and that's exactly what I did over here. So dl dt will then be written as del L del t plus summation over I del L del qi dot plus summation over del L del qi double dot. Okay, so here you can see that I basically tells you that the number of degrees of freedom of the system. Now remember, so this is a useful trick which we will use very frequently in the Lagrangian formulation. That is, this del L del qi we simply replace by ddt of del L del qi, because L satisfies Euler-Lagrange equation for every qi, right? So this is now substituted by this. Okay, and so this term will be ddt of del L del qi dot times qi dot plus this system will be del L del qi dot times ddt of qi dot. So as a whole, the total thing will be summation over I ddt of del L del qi dot times qi dot. Okay, that's exactly what I have written over here. This is a total differentiation. Okay, plus del L del t. So if I take this ddt and the summation interchanged, and that's very easy to understand, that's trivial, then basically we can say del L del t is nothing but dl dt minus ddt of summation over I del L del qi dot times qi dot. And on the other hand, if you write that minus del L del t will be equal to ddt of summation over I del L del qi dot minus L. This quantity is a constant of motion if the Lagrangian does not contain explicitly time. So you understand that if the Lagrangian does not contain one of the generalized coordinates, then the corresponding conjugate momentum is a constant of motion. And if the Lagrangian does not explicitly contain the time, which is the intrinsic independent variable, then the constant of motion is, there is another constant of motion, and that is simply summation over I del L del qi dot minus L. Okay. So for the system where Lagrangian is independent of time, we have, this is an invariant of motion, and we call this curly E. Okay. Now can we see that the above quantity is nothing but energy for usual mechanical systems which are conservative? Well, let's try. So previously we identified for conservative systems L is equal to T minus V. Again we are only considering V which are the function of explicitly Q. Okay. In case where T is a quadratic function of velocities, that is the most usual case. If you remember, when we wrote this, the generalized, the generalized expressions of kinetic energy in lecture number 4, I think, kinetic energy using the generalized velocities, we showed that the kinetic energy in general is a quadratic function of the generalized velocities. Then using Euler's theorem of homogeneous function, I will not go into the detail about that. If you want, I can discuss on this in a tutorial, in a discussion session. But Euler's theorem on homogeneous function of degree n simply says that if you have homogeneous function f of let's say x of order n, then del f del x times x, okay, will simply be equal to n times of f. And that's exactly we have used here. We said that 2 is the number, the degree of homogeneity here, because this is quadratic function, so it is a raised to the power 2. So using this formula we can simply say that the kinetic energy T, when this has when this is a quadratic function of velocities, then del T del Qy dot times Qy dot, then we are taking the summation over all possible, all the Qy dots, okay, that will simply be given as 2 times T. Okay. So actually in Euler's theorem we say that if this is a function, the homogeneous function f is a homogeneous function of order n of all y1, y2, y up to yn, then summation over I y del f del y is equal to nf. That is the the theorem. You can check. Okay. And if you do that, basically again you can say that we are in a condition where v is independent of velocity, so v can be taken into this del qy dot, and we can write this is del t del qy dot as del l del qy dot. So this one is now is equal to 2t. Okay, so if you remember, this curly E was this term minus L. Now this term is 2t. So minus L is minus t minus v. So it will simply give you t plus v. That is the total mechanical energy. So when the Lagrangian is explicitly independent, or rather does not have any explicit dependence on time, the total, and for a conservative system, okay, where the kinetic energy is a quadratic function of velocities, rather generalized velocities, and the potential function is a function of coordinates only, generalized coordinates only, then the total energy of the system is conserved. Okay, so that was the message of this formalism. Okay, so in the next subpart of the lecture we will talk about the symmetry transformation of Lagrangian. Okay, thank you.